May 7th, and this is Nighttime Mathematics Radio. Well, it's a slow night on Twitter, but we did get one question in from somebody. Question asking about how do you take derivatives of inverse functions, because that's not immediately obvious. Turns out, like everything else in calculus, there's a trick to it. So we'll talk about that after the break. So, in the meanwhile, if anyone else has any questions coming in off Twitter, some homework problem that's just not making sense, something your teacher said in Zoom that zoomed right on by, feel free to tweet questions at Night Math Radio, and I'll try to help right here on the air on Nighttime Mathematics Radio. Let's take a few minutes for people to tweet in, then we'll come right back to the show. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, it's a quiet night out here on Twitter, but I still have the one question that came in: is how do you handle an inverse function when it comes to derivatives? Well, let's make this concrete. How do we handle things like taking a derivative of, say, an arctangent? Let's take a look. So suppose we're given that y is equal to the arctangent of x. What is the arctangent? Remember, it's the inverse of the tangent function, restricted to a domain where that makes sense, because you can't actually take the inverse of the tan itself, right? Tan x looks like this. If I take tan x and draw a plot of it, it comes in flat, blows up, blows down, and then does that again and again forever. So this fails the horizontal line test about as spectacularly as it's possible to do so. So this can't be an invertible function. But what we could do is we could say, well, suppose none of this existed. Suppose the function only existed here between minus pi over 2 and pi over 2. Well, then we can do an inverse, because now, as long as we restrict the domain like that, the function really does pass the horizontal line test. We've given it a specific inverse for every possible value. So whereas tan x, and sometimes some books actually write this tan differently. They write tan x is the one that's restricted, so that tan x is a function from minus pi over 2 to pi over 2 onto the real numbers. The idea is, okay, this isn't the real tangent, which takes every value that isn't an odd multiple, I should say, of pi over 2. We'll take this version of tan x, which only exists between minus pi over 2 and pi over 2, because as long as we have that one, we really can inverse. And so that's our arctan here. So the arctan is a function that goes from the real numbers to minus pi over 2 to pi over 2. And I've actually seen people use it for precisely that value. They've seen people use it for values for reasons that have nothing to do with trig and everything to do with the fact that it takes enormously large numbers and maps them to sort of around pi over 2, and enormously small numbers, and maps them to kind of around minus pi over 2. So it has a lot of motion right in the middle. So if you plot arctangent, it looks like this. The whole thing sits between pi over 2 and minus pi over 2. And it starts very close to minus pi over 2, comes on up, and then shoots out like that. So it separates values close to 0 very nicely, but very, very large positive numbers and very, very small negative numbers just get doors flattened out. And that's a really useful property that people use all the time for just that. That said, what if I want to find the derivative of this thing? How do I find dy dx? And the answer is, we play a trick, as with everything else. What we do is, instead of saying y is equal to arctan x, let's write it backwards. Let's say x is equal to that cool tangent function we know of y. And now let's take a derivative of both sides with respect to x. Well, the derivative of x with respect to x is 1. We know the derivative of tangent because as long as we're in the domain, which we are, because after all, we've just inverted this thing, so we know that x sits between... Sorry, we know that y sits between minus pi over 2 and pi over 2 because it was the arctan of something. This thing is just going to be secant squared y. But now we have to use the chain rule, because after all, we're not taking a derivative with respect to y, we're taking a derivative with respect to x. So we now need to multiply that by dy dx. So dy dx is equal to 1 over secant squared y. And you say, well, that's great, but I've written it in terms of y. And usually when I take a derivative of y with respect to x, I'd like my answer to be in terms of x, please. Well, now we use a trig identity that we've been keeping in our back pocket up till now. Remember, there's a really useful trig function, tangent squared of a value of, say, y is equal to sine squared y over cosine squared y. So if I add 1 to that, I get that plus cosine squared y over cosine squared y. The numerator sums up to just 1, because over sine squared anything plus cosine squared, that thing is 1. That's Pythagoras' theorem. So this turns into secant squared y. So I can rewrite 1 over secant squared y as 1 over 1 plus tangent squared y. Remember, tangent y is just x. So that's 1 over 1 plus x squared. And this kind of game is the trick to finding the derivative of every inverse function you'll ever run across. It's, okay, let's write it without the inverse. Let's write it in terms of the original function. Differentiate both sides with respect to x. Solve for dy dx, which will pop out from the chain rule. And then figure out how to massage the answer back in terms of x again. That's fundamentally how you handle derivatives of inverse functions. That's how you handle tangent, that's how you handle arctan, that's how you handle arcsine, that's how you handle arccosine, that's how you handle all of them. And that's where those strange formulas on the inside back cover of your book come from, ultimately. It's playing exactly this game. This is Nighttime FX Radio. Let's take a few more minutes to see if anyone wants to chirp on Twitter. And if not, we'll call it a night. So for the moment, sit back, dig through your math, and listen to some of the strangest loops that Apple stuck into GarageBand. This is Nighttime FX Radio. Well, everybody, it's looking like a quiet night out there, so I think it's time to end the show. So in this weird world where the classes are all on Zoom or have stopped, but the homework just keeps going on and on and on and on, tune in to Night Math Radio every night, except nights where there's nothing to talk about, and we'll be here Pacific Time, 9 p.m. Try to answer your questions live on the air. So for the moment, good night, everybody. Stay safe. Keep doing the math.